Hey, today we're going to work on lesson 6.6, applying volume concepts. So we've talked about volume a while back, but we're going to do a little more with that today. So our objectives today are that you want to be able to apply your knowledge of volume concepts to calculate the volume of a building, understand concepts of volume, and relate volume to multiplication to division. First, we're going to solve some number stories here. First one says Sasha has 12 golf balls. She lost 1/3 of them. How many golf balls did she lose? So if you remember, we could write this as 1/3 of 12. So a fraction of a whole number. And I could simply change this to multiplication and put my whole number over 1. And I multiply across and I get 12/3, which is the same thing as 12 divided by 3, which equals 4. So how many golf balls did she lose? She lost 4. And that makes sense because she had 12 and she lost 1/3 of them. Let's look at the next one here. It says Cho has 25 sheets of colored paper. After he made some crafts, he had 1/5 of the paper left. How many sheets were left? Okay, and I see of there again, so he used 1/5 of the 25. And again, I can change that to multiplication. And I get 25/5, which is the same thing as 25 divided by 5, which would be 5 sheets left. So now you're going to look at the next ones here. So go ahead and pause the video and solve both of those. Hopefully you had a chance to solve those. And so if you looked at the problem, you could see a chef has 8 pounds of apples. He used 1/3 of them. How many pounds did he use? So it's 1/3 of 8. And then you would solve that. And then the next one here, Elise has 12 songs. She listened to 1/5 of them. How many did she hear? So again, you would write the number model 1/5 of 12 and then solve. And on these two, you wouldn't get a whole number, you would actually get a mixed number when you divide those out. Now, you do not have the Math Masters page if you're at home, but here's a picture of the tower that we're going to be talking about how we can estimate the volume of it today. So again, you can see the picture there. So that's in reference to the tower we will be talking about. So until 1988, Willis Tower in Chicago was the world's tallest building. The building's base covers 50,625 square feet, and the building is 1,450 feet tall. Look at the photo of the Willis Tower. Would multiplying the area of the base by the height of the building be a good estimate for the building's volume? So first, I know that that's going to be the base, and it's 1,450 feet tall. And so they're asking us, would multiplying the area of the base by the height of the building give us a good estimate of the volume? And if you remember, we have two formulas for volume. You could say base times height, or you could say length times width times height. So let's go back and look at that photo for a minute, and I want you to think about that. Do you think you could take the base, which would be the bottom, and you can't really see it down here, but they're telling you the measure, right? The base would be where it's sitting on the ground, and then obviously its height would be from the base or from the ground all the way to the top there. So think about that. With those given numbers, could we come up with a good estimate on the building's volume? And so obviously if you're at home, it's kind of hard for you to share your thoughts, but you could write those down. But I want you to think about that. Does that work or not? Well, we know multiplying the area of the base by the height of the building is one way to get a rough estimate of the volume of the Willis Tower. It would give us an overestimate. So it would be a little bit greater because if we look at the structure of the building, you can see there's other parts sticking out here. So it wouldn't be exactly the same, but it would give us a good idea. because the base isn't completely one rectangle. There's different additions on the side there. So it would end up being an overestimate because we would be adding in more on the base than we really needed to. So can you think of another strategy that would give a measurement closer to the actual volume? So take a minute and think about that. If I wanted to find the actual measurement, let's say I was to do a report on that, or maybe I'm an engineer and I need to know what the exact volume of the building is. Can you think of any other strategies? So go ahead and pause the video. You can jot yourself some notes. Okay, so hopefully you've taken a moment to think about that. And remember how you estimated the volumes of musical instrument cases earlier this year? So I think we did a guitar case and some other odd-shaped instruments. And instead of the cases being like having the curves, we just made them into rectangles, which goes with the additive volume. So today we'll revisit and extend methods for calculating volume from given measurements. Okay, so this is not a scale model of the tower, but it does give you a kind of visual there to see how it's set up. So you can see when you look at this model, you can see over here, here, here. They have some different heights. They also would have different measurements there, right? So the base might be the same, but when we calculate the height, we only gave you one height instead of a height for each of these. And again, not a scale model, but it does give you an example what it might look like with cubes. So obviously, if you're home, it's kind of hard for you to share your strategy, but you can think about this. Remember, you want to be both accurate and efficient when finding the total volume. So that's important that we're accurate. And accurate means we're getting it right. We're as close as we possibly can be with the numbers that we have. We don't want to try, which it's not the same thing as an estimate when we find the actual. And efficient means you're finding a strategy or a way that you can move quickly with that and still get the correct answer. Okay, so think about these questions. How are you keeping track of which modules you have found the volume for and which modules are still left? Okay, so when we talk about volume, if you're breaking up a figure, like with those cubes on there, or even on Evaluate when we get problems where we have to break it into two parts, we could think those as modules or sections of the building or of the box. Did you find that the taller modules have greater volume or smaller volume than the shorter modules? So think about that. If they have the same base, are the taller ones going to have a greater volume? Are they going to take up more space? And does my volume answer make sense? So that's a big thing. Sometimes people come up with these volume problems and answers, and it's way out there, especially on Evaluate. And really, it's not reasonable with the given numbers. So you want to be very careful with that. So those are great questions to ask yourself when you're solving volume problems. So think about these questions for efficiency. Do you notice any calculations you're doing over and over? I think that's a really big thing, especially on the Evaluate problems with the irregular figures for volume. I think a lot of us struggle with those because sometimes we're doing the same thing over and over, or we're not keeping track of our work and what numbers we've used and marking them off. Do you need to do that calculation for every module or every section? Okay, that's something else you need to think about. So you need to think about these questions for efficiency as well. How could you use the calculations you already did to help you finish finding the volume of the tower? So if you were measuring a tower and you made your own out of cubes, how could you finish it? Find the volume of the tower. So are you writing down your calculations for each section? Right? If you have two sections that are the same, do I really need to recalculate those if I know they're the exact same? Okay, so now you're going to use a calculator to complete your math. Okay, so it says make your posters, sure your posters are clear as possible because your classmates will be looking at the posters to try to understand your strategy. That won't be happening if you're at home, but we are going to go back up to the numbers in just a second so you can do some calculations. Okay, oops, sorry about that. So you want to go back up to here. And now I want you to take these numbers here. And remember, we said we could do base times height. So we have 50,625 square feet for the base. And remember, it's base times height. And 1,450 feet. Now, just even taking those numbers and estimating, I know I should be, if I look at it, I could say 50,000 times about 1,000. So I know I should be somewhere around 50,000, probably more than that because I have 625 times the 425. So I would estimate on there somewhere between 50 and 60,000. But go ahead and take a calculator and multiply those numbers. So we know we're doing base times height. And remember, this is an estimate because they took the one height, and when we look at the image, we can see that there are multiple sections here that have different heights. But they took the highest point from the ground. But go ahead and take those numbers, calculate those with your calculator. So pause the video now and go ahead and calculate. You can use a calculator in your Chromebook, or if you have your own calculator or on your phone or tablet. But go ahead and use your calculator to multiply the base times the height. Okay, so hopefully you've had a chance to do that. So let's see if your numbers match up to mine. So if you remember, I gave an estimate. I said it would be around between 50 and 60,000. I was thinking a little more than 50,000. And when you put it into the calculator, you would find it's 53,578,125. So I actually misspoke before on the estimate. It should have been in the millions, and I said thousands. Okay, and so that is an approximate volume, and it's not exact. But we took the information we were given and we did the base times the height and made our calculations. Now, again, you can see with the tower here, different heights, different sections. This would be where you would actually want to do additive volume if you were calculating the exact one, because the base may be the same for the whole building, but the heights are different. So you would have to break that into different sections. So here's some strategies you could use to find the volume of that. You could record the length, width, and height of each of the 9 mega modules. Okay, and that just means the 9 different sections of that building, how it was sticking out on the side. You could use V equals L times W times H, which is the formula. This simply means volume equals length times width times height. Then you could add the volumes of each module to find the volume. Total volume, which is what we do on Evaluate, and we've done before. When you find the volume of irregular figures, you dissect it into different sections, and then you would add each of the volumes up. So again, module sounds confusing, but it just means each shape or each section you broke it into. You could also do what we did because they gave us the base. You could say base times height to find the volume of each mega module. Each of the modules have a base with the same area, 75 feet by 75 feet, which equals 5,625 feet squared. Then you can multiply this area by the height of each module, recording the volume of each module, add the 9 volumes to find the total volume. Now, they gave us an estimate, but we could do that. We could take each section, all 9 different sections that are different. We know they have the same base, but their heights were different. So we could calculate all 9 of those and then add them together. Thankfully, on there, they did some estimating to help us with that. So something else you could recognize that some mega models have the exact same dimensions. So if you see 2 or 3 sides that are exactly the same, then you know they're going to have the same volume. So for example, there are 2 modules with dimensions 75 feet by 75 feet by 1,450 feet. Use either volume formula to find the volume of one of these modules, and then multiply that volume by 2 to find the total volume of the 2 same size modules. Repeat for other groups of same size modules and add to the total volume. So basically that's saying if you know that there are 2 or 3 sides that are exactly the same, that you could just multiply that volume by 2. If there's 2 of them that are exact same, you could multiply it by 2 and add it into your total volume. So now, go ahead and pause the video and turn to Math Journal 2, page 212. Okay, so you should be on 212 now. It says what is the approximate value or volume of Willis Tower? That's where you're going to take your base and your height that we looked at, and you're going to go ahead and write in the cubic feet. So again, you're going to take your number that you got from multiplying your base and your height, and you're going to put it in there. And then you're going to describe the strategy your group, or in this case, you as an individual, used to estimate the volume of the Willis Tower. Okay, so did you do base times height, or did you try to do something else? And do you think your group, or in this case you as an individual, could have used a more efficient strategy? Explain at least one way your strategy could have been more efficient. So if you remember when we looked at some of the sample strategies, they were talking about adding all the different sides together, and then, or calculating each of the sides, and then adding them all together. Is there a more efficient strategy, such as if we know if we know we have two sides that are the same, calculating the volume of one and using that measurement? Okay, and then to finish off the lesson, just to help you review with decimals, you're going to play Decimal Topic online, and you can find that on the McGraw-Hill website.